Hello everyone, we're Group 3, and today we are going to share our research on spatial temporal analysis of urban vitality and its drivers, based on mobile signaling and multi-source data. Our approach has three main steps. First, we processed mobile signaling data to extract where and when people stay, and these are called stay points. Second, we applied spatial temporal clustering to analyze these stay points over time and space. And finally, we explored the driving factors behind urban vitality using machine learning models, especially random forest. And to start, we used the dbScan clustering algorithm. Two key parameters here are the neighborhood radius and the minimum number of points, and this impacts the clustering results. To find the best radius, we used a key distance graph. We look for the elbow point in the graph, the place where the curve suddenly steepens. And that means before this point, the data points are close together and probably form a cluster. After this point, they are too far apart, likely noise or from a different cluster. And here is our code for the k distance. Based on our k distance graph, we found this elbow at 0.027. So we used this number as our dbScan radius. Here's the code we use to calculate this and plot the graph. After setting the parameters, we performed clustering separately in both spatial and temporal dimension. To demonstrate the process, we use industrial land as an example, and here's our code. The colorful plot shows the clustering result. Each color means a different cluster. The output is saved in an Excel file. We added a new field to the file to label the cluster number. For example, if a point belongs to the cluster 1, the new field will be 1, and so on. We then visualized the clustering result in ArcGIS Pro. Using the quantile method, we categorized urban vitality into low, medium, and high levels. And here's a zoom-in view of a selected area, showing how urban vitality varies locally. And this gives us a clearer view of the spatial distribution of urban vitality. And so far, we've identified areas of low, medium, and high vitality in time and space. But what are the key drivers behind these patterns? And this is where random forest comes in. First, we calculated the weight density of different POI types using inverse distance weighting, or IDW. It assumes closer points have more influence. We apply this to each vitality zone. Then we use random forest to analyze which POI types had the biggest impact in each area. After running this model, we got an important score for each factor, like medical services, entertainment, and so on. Here's the final output. It shows how different features contribute to the vitality level in each region. We use these results to create another visualization, so we can clearly see what's driving urban activity in different zones.